Mr. Santosh from CD Pilani lab. Both of them are senior scientists over there. So she will be covering especially the MEMS related devices, MEMS devices, and related to that, how the practical aspects of real time things are there. Those things will be covered by both of the expert speakers over there, with some demo to the lab sessions, that how those type of devices you can create in your labs with ticket softwares and all. So that part will be covered by both of the speakers. So I welcome you, sir. Both of you are welcome. And it is over to you, sir. Please start. Thank you, sir. Sir, can you hear me?
Yes, ma'am.
Your voice? Yes, sir.
Yeah, the
Thank
screen
you.
is visible, ma'am?
Yes, sir, it is visible.
Yeah. So, good afternoon. My name is Jay Gopal Pandey, and we both, myself and M. Santosh, we are scientists here, and we are working in the field of VLSI design and associated sensor development. So now we are going to start a session on evaluation of CMOS sensors, applications and challenges. So Santosh is expert on the he has either wide experience and hands-on experience in this field. So we both together will conduct this session. So please, now we are going to start.
Good afternoon all. So, we will try to see how exactly sensors are coming into role for our day-to-day applications. And we will try to understand CMOS sensors also in the past. Can I know the type of audience we have? You have the background of fabrication, right?
Sir, audience are especially faculty members, researchers, PG candidates from physics background, electronics and electrical background, sir.
So that
So
means the requisite is there.
there are UGPG candidates as well, but especially they have been attending this particular session for something they can that can help them to their projects, their research papers, and especially contribute to the research.
Fine. So it should be like this. There are many things. We will cover many aspects because I have some good amount of time. For any query, please stop me so that I can clarify your doubt. I will try my level best. Okay. So start. We can start now. So our path will be like this: that we will first understand why we require sensors. Then we will try to understand the current sensors, majority of sensors, like MEMS type of sensors and all these things. What are their structure, characteristics? What are the issues? Then why we need CMOS sensors? What exactly is not available in current MEMS sensors that we have to move towards CMOS sensors? But it is not that everything is possible in CMOS. So we will also understand that with a few case studies, or maybe one, two case studies. Then we will try to make a final conclusion and we will identify which type of sensors can be in CMOS, which cannot be in CMOS, and they have to be done in MEMS or other technologies. And we will see the future goals and future conclusion. Majority of the session will be, and this is not on slide, whenever it is required, then only are slides. It will be, I will be using the soft notes. Yeah. So these are very day-to-day things that we use nowadays. This is the board of a mobile phone board. You can see here that there is a range of sensors starting from MEMS, accelerometer, gyroscope, magnetometer. Like a simple example can be that let us say I want to rotate my screen. When I am rotating my mobile, you can see that automatically the screen will adjust itself because there is a on-chip accelerometer is there. Similarly, if you see the automotive scenario, you will find a range of pressure sensors. Example, like let us say you are riding a car on the plains, and once you are going to mountains, let us say, on a mountain, obviously your pressure is less. So if you put a barometric sensor, you will see that your pressure is less. If pressure is less, then obviously the amount of oxygen that is available is less. So based on that, you have to automatically change the air inlet components. Otherwise, your vehicle will not work efficiently. So these type of sensors are nowadays integrated in the vehicle itself, so that they can seamlessly work in any terrain, doesn't matter, which was not possible in previous generation vehicles, which were purely mechanical carburetor sort of things. The third thing, this is an example of an app. This is basically a sort of quadcopter. You can see that in a quadcopter you need a IRE sort of thing. IRE is nothing but basically a navigation tool, which has a set of 3-axis accelerometer, 3-axis gyroscope, 3-axis magnetometer, and a pressure sensor. And the data from all of them are combined together to control the flight path of this quadcopter. Just to give an example, to have a feel, you just do this. You can see my screen, right?
Sir, your screen is not visible. It got disconnected currently.
Not disconnected. Okay. Now it is visible, right?
Yes, sir.
Okay. I'm giving you a few examples of actual sensors, how they have been used in the current scenario. So what you can see here is basically the modern tire pressure monitoring systems that are installed on our cars. So if you can see here, each tire is having a pressure sensor. Basically, these are all pressure sensors, and they are communicating to a local gateway, which is displaying the data on our console. Okay, they are using some sub-gigahertz protocol uh, to minimize the power, because obviously the range is not. Have a analog cell structure and a RF structure, everything on a single chip, and that is communicating to the local gateway. In this video, we are trying to explain that these sort of applications which are currently used in our day-to-day activities, which you must have seen, I believe so. In this way, you can see the tire getting displayed on your consoles. Now, the final thing that they are trying to show is pushing these values to my parameter, to the IM and the ECU basically, so that I can control the brakes and all those things, which are usually not present in our cars used in India. They are all available in high-end cars. The second example I am trying to show is this one. Fine. So here, what we have done is, basically, we will not go into the controls. The point is here we have used a type of sensors like we have a gyro and an accelerator to stabilize this platform. And we can see that in real time it is able to control the platform motors in such a manner that this water is, this cup is not falling down. Okay, so that's it. Now we will come back to this. So what we are trying to understand here is what exactly the sensors are. If you see here, this is basically a MEMS pressure sensor architecture that we are trying to show. This is a Wheatstone bridge configuration that we are trying to see. And it has 4 registers that have been implemented on this diagram. And this and different type of structures are there. It could be circular, it could be, this is the case of the square diagram. And if you see here, the registers are implemented here, right? Here at the R1, R2, R3 and R4, these are the resistor points. And when you are trying to apply a pressure, this diaphragm, like here in this, in the cross section, you can see that wherever you are applying the pressure, there will be a deflection, and due to the deflection, it will change. Again, it is better to show it. It's more or less like this. But let us say I have a diaphragm like this, and I have implemented resistors here. And let us say that my diaphragm is changing. That means whenever I am applying a pressure P on top of that, if I see the side view, I will have a deflection like this. So these resistors will experience compressive and tensile stress. So if I draw the electrical equivalent of it, it will be something like this. So 2 resistors, they are changing in opposite direction. So if you see this output will be a differential output. If it is a balanced bridge, so obviously you will get a differential output at least 2 output, OP1 and OP2. And this is your VDD, and this is your output. Correct? The same thing we are trying to do here. But remember, this structure, this is your diaphragm. This could be of different structures. There could be a case where I have a circular diaphragm. I could have a case which is a square, and there could be a case which is a rectangle. This is also possible. So there are 3 cases which can be done to implement, when all these 3 can be used to make a pressure sensor. And the pressure sensor, whatever is the structure, it doesn't matter. The principle is like this. So you have a structure like this. Then you have a structure like this. And when you are applying a pressure P, this will have a deflection, something like this. So due to this deflection, your resistors will change. And due to this change in resistors, you will have a differential voltage between V1, this is nothing but V1, and fine. So this is what is happening. I hope it is clear. So the same thing we are trying to explain here. Now, how will you test it? So the point is, once these sensors are there, then we need to do some measurement also. So this is how we do the measurement. So what we do, we apply, this is basically a pressure controller. You can see, I hope there is a yellow color box in there, right? So that is the pressure controller. And this is basically a temperature chamber in which we are trying to put the sensor. And in this, we try to apply pressure and we change the temperature and see through the DMO what are its characteristics. When we do, we will get something like this. So what is happening here? It is basically this is the differential output. If you see this curve, this is basically the differential output between OP1 and OP2. But when I am trying to experience, so apply some temperature over it, there is a change. This change is because your the resistors themselves, they have temperature dependence. As a result of which, you will have deviation. That is what you can see here. The same can be seen from the differential output point of view also. So, to explain this, it is like this, that ideally, this is your pressure and this is your differential output in terms of millivolt. You should have an output something like this, which is very linear. But due to the temperature, what will happen? You will have an offset, fixed offset, neutral. This is valid when you have done the designing of this property. If the placement of these resistors, and if the resistor placement is perfect, that means you will have a fixed offset, something like this. Now this can be compensated, this is not a great deal. All you need to do is you have to do modification at circuit level and it will work. If, as an example, I am just trying to explain it, that how it in real world works. Now we know very well that, let us say I have a circuit something like this, that I have a pressure sensor. Output is differential, obviously, because this is differential output. So when I am feeding this to a IA means instrumentation amplifier, and so I will have a single-ended output voltage, because we know IA output is single-ended output. As CMRR of IA is very high, and we know that, is roughly more than 110 dB. Due to this high CMRR, we have ensured that whatever the common mode noise is there, they are getting distributed. Now this IA is fed to a sort of level shifter. The reason behind it is, if there is any offset here, there will be certain offset, right? Because you can never make four resistors which are completely equal. If there are unequal resistors, that means R1 is not equal to R2, is not equal to R3, is not equal to R4, let us say. So this will give rise to an offset. to compensate that offset, we need a level shifter. And this output is then fed to a ADC. And this is actually, this is one digital output. Now, when I am having such a configuration, let us say that you have a change in, that means you have a fixed offset. So what you need to do, all you need to do here is change this bias voltage. Device. Right? By changing this bias voltage, we have taken care of this offset. Agreed? Is it clear? Or should I go a little bit more detail into the maths?
Sir, audience are not given the control of the mic, so they can only type in the chat box, sir.
Then at least drop a message in the chat box.
So I request audience to please type a message in the chat box. Whenever sir is asking something or you have any query, please type in the chat box.
Yeah, because it's difficult to explain all details. So based on the requirement, I can just go to the details. Okay.
Or you may tell that what specific thing you would like to discuss, because they are having very vast knowledge, and whatever time we have given, it can be very short to share all the knowledge. So if you want something specific to be discussed, you may drop in the chat box. They will discuss that.
Yeah, that would be better in fact. If you can drop something, that will be meaningful for me also.
Yes, sir, please. Please proceed, sir, as per your plan.
Yeah.
If it is interactive, it will be beneficial for both. So we will be, as we are having experience in this field, so we will be happy to answer your queries.
Yes, sir. Right now they do not have any query. I hope they will be having the query whenever we will proceed, and they will be typing in the chat box, sir.
Yes, ma'am. Sure.
Fine. Then, so the point is that that means that any sensor fixed offset. So this is nothing but a fixed offset. I can see. So this is a fixed offset. Fixed offset can be compensated by just adjusting this bias voltage. So I don't need anything. Now, what about a condition like here? You can see here. You have 2-point shift is there. Like you're not able to get that. Let us say I have a scenario. You can see in that graph something like this. Let us say. That means if I take a graph, it is a second order nonlinearity. That means you cannot, it is not a fixed offset. It is a nonlinearity is there. Now this cannot be done with this V bias voltage adjustment. This will not work here. It will not work. So for this, what you have to do, you have to go for different mechanism. The mechanism can be like this, that you have a pressure sensor, output is differential, feeding this to an instrumentation, then going ahead with a level shifter, we are going to a ADC. This is generating a digital bit. This digital bit is going to a controller. And in this controller, and we are sampling the digital bit and taking a DAC. And feeding here. That's it. Okay, something like this. Okay, so what has happened? So what is happening here? You are basically, you have developed a control algorithm. You have a control algorithm. What it is trying to do, it has divided the entire characteristics into piecewise. Okay, and it has calculated the coefficients. Based on these coefficients, it will generate automatically a V-bias to make it linearization. And that V-bias will be generated through this DAC and fed to the level shifter. So in this manner, this will be corrected, something like this. So the point is, the sensor, if the sensor is manufactured properly, then you just need this much of circuit. This is your best case. This is your simpler circuit, no feedback. No feedback. But this is with feedback. The reason is my sensor is not perfect. So it turns out that everything is important. The only parameter that is important is how well you have made this sensor. If this is designed properly, no problem. Otherwise, there will be issues. Now again, let us jump to this. So in the measurement, if you see here, we make sure that we capture all the nonlinearities. Like here, we are trying to see that between compensated and uncompensated, how exactly my nonlinear variation is changed. Okay. Because these parameters are important, because your sensor is required to operate in a certain range of temperatures. Now, as we have discussed previously, that these resistors, these MEMS-based sensors, we are using what? We are basically using polyresistors. These are basically the resistors which you have to implement, right? Now, resistors can be implemented in, how would you implement resistors? Now, any resistor, it could be poly, metal, or diffusive. Measure. So, how will you make poly? Poly means basically you go ahead with a poly deposition. I'm not going into the detailed steps, but if you see the top side of it, if this is your silica, you go ahead with the oxide. This is your oxide. Then you go ahead with the LPCVD. This is your poly. You know very well that deposited poly has very high resistance. So this resistance has to be brought down. So what will you do? You go ahead with the diffusion process. Go with the diffusion process. So that by this you can bring down its resistance to some kilo ohm range. That is the target. So this is the process of poly. How will you go for a metal? Metal is very simple. You take silicon, throw a oxide, then you deposit a metal by sputtering. You know very well that metal has some sheet resistance. to exploit that to generate a register value. Remember here you don't have option of no option of diffusion, right? But you have a diffusion option here. So here the major demerit is area. And if you are targeting a large R, your area will be very high. But here if you are targeting a large R, all you need to play is the diffusion. That's it. It will work. Now the second thing is diffusion. Here, what you try to do is you take silicon, then you make a diffusion layer of let us say M plus, and then you make a contact here and here. So basically you are making a resistor, extracting a resistor out of it. Right? So here, this is also done by the process of diffusion only. So here we are using a diffusion process. But remember, this is sitting on the silicon. So there will be a dependency on voltage. Apart from that, this is more or less similar to a polysilicon. So it turns out that this and this can be used to implement big resistors and big value of resistance. But this cannot be used. So, and in our case, we have majorly used poly-based resistors for the fabrication of MEMS devices. Okay. So, in poly-based resistor, using LPCVD, you can implement resistors. But remember, polysilicon has some other issues also. So they are nothing but it works on the principle of piezoelectricity, right? So you need to have actually three piezo coefficients, pi 11, pi 12, and pi 44. They determine that what type of piezo behavior the material will demonstrate. So based on that, you estimate the resistances. That's not really it has been mentioned here. So it turns out that you need to use all these models to estimate its behavior with pressure. It also includes a certain degree of nonlinearity, and it has strong dependency of temperature also. That is what we can see here. That with the temperature, your output variations change, and the output is nonlinearly changing. See, most important thing, if I have something like this, my pictures are not that good, assuming that my spacing is fixed, okay, this is fixed shift. But what about this? Now this is not good characteristics. That means for every temperature, I need to get a calibration curve, and it is difficult to compensate it. This is not at all a good characteristics. So this is one of the major problems with these polysilicon-based sensors. Taking into account of this, the second example that this is, remember, pressure sensor is a static sensor. There is nothing called as the dynamic behavior. I got to understand. Static dynamic, let me explain what do you mean by that. If I take a sensor, it can be divided into static sensor and dynamic sensor. What is the meaning of it? Static sensor is a pressure sensor. What is a dynamic sensor? It is nothing but an accelerometer. So the point is, what is the basic difference? This output will come only when input, and if there is a change in input, then only you will have a. I will say like this. Will give rise to change in output, and this has to be continuous. So if you do a spectrum, you will have a. If you do the FFT, you will have a spectrum. Whereas in a pressure sensor, there is nothing like that. They always operate at DC condition, but this operates at certain frequency or a band of frequencies. It operates at a certain fixed frequency, it operates at fixed or a band of frequencies. So this is the basic difference between them. Okay. Now, till now we have discussed about static only. Now we will see the dynamic behavior. To understand dynamic behavior, we have gone ahead with an accelerometer. This is basically an in-house designed and fabricated accelerometer that is being, you can see, mounted on the shaker. Now the shaker is basically generating a specific frequency which can be used to vibrate the sensor at a specific frequency. And based on that, we will have a differential output. And this is the circuit that is usually used. So here what is happening? The shaker is powered by a waveform generator, which is nothing but AWG, arbitrary waveform generator. And the sensor, as we know, it is based on piezoresistor principle. So basically, the anchored proof mass is there. And on the bridges, we have integrated the resistors. So they are basically the sensors. The output is then fed to a level shifter. So why we are using a level shifter? The reason is so that I can compensate the differential output offset, because these sensors have inherently very high offset, because due to the fabrication related issues, we can never match the resistors. Then we feed this compensated output to a instrumentation amplifier, and then the output is getting fed to a MSO to capture the spectrum, and to a digitizer to capture the minor variations, because MSO has limitation of resolution, and a LabVIEW based platform where we try to do the transient data storage quantity. And we put a reference sensor also so that I can capture its output in parallel to our in-house sensor. So both the data are captured using the NLPXL LabVIEW platform. And so here you can see basically what we have done. Let me explain here. So in order to understand a dynamic sensor, we have used a accelerometer. This is a out of plane accelerometer. That means if this is my sensor and if this is my axis of motion, then it is sensitive to this direction only. Okay, this is out of plane. And here what we have done, we have taken a test platform. This is our DUT, and in parallel to that, we have kept another commercial sensor on the same platform, and this entire platform is getting vibration from vibrated through a shaker. Okay. And this shaker is getting the signal from a function generator. So I know, let us assume that I am generating a specific frequency f in. So the idea is these two sensors will also generate a frequency f in when f out, and ideally f in should be equal to f out. This is what is expected. And the degree of deviation shows whether my sensors are perfect or not. So the same thing has been done here, and these are the various circuits that we have connected. Now if you see its output characteristics, so this is how it is there. This is basically a 50 Hz. In the top graph, this is the 50. You can see that both the peaks they are matching. You can see a red color circle is there, and you can see that that has reading around 100 Hz. What we have applied is around 100 Hz. And to reflect the same thing in terms of time domain signal, you see here that both the signals they are matching. Yes, there is a phase difference, obviously. But the sensor output is noisy because these sensors, due to their high values, and we have used a lower order low pass filter due to which the noise is getting possible. But it is working. But the important thing to observe here is if I remove my frequency from the shaker, the output will be flat because of this is dynamic sensor. That you must understand. The same thing we have also, with the different frequencies we have shown. Now important thing comes here. See, as we saw in the previous case, here also, if we do a frequency sweep and observe my output voltage, you can see here that it is majorly a fixed offset. Even if I change my frequency, this is good. But whereas, if it is not fixed, then our problem is different. Now, let us say that I am applying a frequency, input frequency, and I am applying this to a shaker. This I am applying to a shaker. And this is generating the output frequency, which is, let us say, delta H plus or minus Fn. So this is the condition. And we know very well that in our previous case, as we know very well that in our previous case, what has happened? We have used a pressure sensor, which is nothing but a, a fixed output voltage, right? So in that case, even if I am applying as there is no frequency component is there, but here when there is a frequency component, you will have multiple voltages that will come into picture. How it will come into picture? Let us try to understand that. Just a minute. Delta V, in the case of pressure sensor, if I see, what is delta V? Delta V is nothing but V supply into right? This is the case. Now, V supply is assuming that my V supply is a fixed value and it is not having any PSRR related issue. Here the assumption is my PSRR is good. So this will generate it. That means this is more or less fixed. Agreed? And here the PSRR is good and my resistors are ideal. Okay? So under these two conditions, this equation will be good. But if I see a overall output equation, how exactly this will be there? Then if I see from this point, let us say at this point I am trying to understand that what is my equation at this point? Let us. It will be whatever you have supplied, that will be by 2 because it is a resistive divider, right? Here, this is the matching resistors. They are all R. That means if this is VDD, this will be VDD by 2. Right? So we supply by 2. Delta V, this is sensor. Sensor. Okay. Gain of instrumentation amplifier. Okay. Gain of level shifted. This is because that is the put value. That's why it's so plus Agreed. This is the equation. But here it is under the case of static. But in this case, when I have a change in frequency, things will not be like that because there will be a delay term will be there. So due to the delay term, this delta V has to be a frequency component. That means you have to include this term here. Now when you are trying to include this term here, if you solve this equation, you will have higher order terms. That means if I try to do the plotting of this, we will have, this is your ideal case, you will have something like this. Now, if you try to fit this, it is more or less like I have to do multi-point calibration. Agreed? Whereas in this case, usually a 2 to 3 point calibration is enough. Usually. We'll do 2 point calibration, this is enough. But here it will not work. So what we try to do here, we go for a lookup table based calibration. It's not easy, it's very difficult. So with that, if we again switch to this, so these are the issues that we can see. So what is the observation that we can see? So the observation is that my raw output is of the order of few millivolts and it is highly sensitive to temperature and limited resolution and highly noisy. Why that is happening? Because it is a structure which is implemented in most probably how much? The maximum show 200 micron by 200 micron. So this sort of structures where its fundamental mode is we expect to be one. The maximum mode should have the highest contribution, but it doesn't work like that. It has other modes also. To explain that, you should see this video to have a better understanding of what I'm trying to say. I got this video place. You can see the video, right? The video is visible, right? Hello. So in this, if you see here, the actually what is happening? You are applying a pressure, and the pressure is getting applied on the diaphragm, and the diaphragm is getting pushed down. That is what you can see from this equation. But remember, this is the fundamental mode, and we are talking about the fundamental mode. But if you try to see the higher modes, you will get other modes of vibration also. Like this is another structure. So, if you see here, you can see here, right? So basically, this will give a better picture. You can see that the structure is actually moving up and down, up and down. So this is the fundamental node. But if you go to higher nodes, it will have other modes of vibration, right? Now, they will introduce nonlinear, which is very critical in case of the dynamic sensor. That's why, if you see here, in the previous case, just see, if you see here, the power is getting distributed over all the frequencies. What is the meaning? The meaning is, ideally it should be like a monotonous frequency. But it is not so. It is getting distributed over a range of frequencies. What do you mean by that? Meaning is, ideally, if I do a frequency spectrum over, if this is my frequencies, I should have something like this. Stricter, it will be like this, something. Okay. And this is my fundamental power. But what is happening? I am getting something like this. The meaning of this is, I have this fundamental frequency. This is my fundamental. But other frequencies are also having sufficient power. As a result of which, the overall power has gone down. Ideally, it should be here, but it has fallen to this point. Fallen to this point. Now, this is because of these powers. So this implies that my design is bad. Okay. So as I said, that it is very important to know how to characterize these circuits, and that ultimately says that to what extent I can operate. Taking these things into consideration, so the conclusion from at this point is that my output is noisy, that as we can see that it is due to the resistive noise. Why it is noisy, that also we can see. See, all these are polyresistors, right? This is a polyresistor, where this is your contact points. And if you see, what is its noise? This is nothing but a polyresistor means its noise spectrum is more or less a white noise. This is white noise, right? And what will be its amplitude? It will be nothing but, agreed? And this resistance value is nothing but depends on what is your absolute resistance, and this is your operating temperature. That means with the temperature, your noise will go up, and with resistance also it will go up. And these MEMS sensors, they are usually of bigger size. To enhance my piezo behavior, what we try to do is, they are usually made big, of typical dimension of, it could be of 30 micron by 100 micron, this sort of thing. So in that case, my overall area is going up, as a result of which my resistance will go up, as a result of which this will go up. Now, this will go up means it is nothing but noise. That shows from where this noise is coming. Highly output noise. Limited resolution. What is the meaning of it? Meaning is, as we have seen here, again, come to this point, take this structure, again at this point, if we see here, what was our equation? We had said here, this is the case, right? Delta V sensor, it is getting multiplied by gain of the IA and gain of the level shift. Again, let us come back to this. What is happening here? Delta V into gain of IA into gain of level. Now remember, if this is delta V plus or minus, let us say some fraction, let us say x voltage, x. Now, this entire term is getting multiplied by this. And what is the typical value of this? If I say in volt by volt, it is roughly more than 150. That means I am actually multiplying the noise. Now, if the noise is high, what will happen? So your resolution will go down. Because of that, this is the statement we have said. A limited resolution. So, in order to remove all these things, what you need to do, you need to change your architecture. This is not going to work. This architecture will not work. This architecture will not work. What you need to do, you need to so this is your progress acceleration. Then you have experimentation method. Then you have a level shifter. Then you go for a low pass filter. Okay. So what it will do? It will cut off after this. So any high frequency noises, they will be removed. But this is also not sufficient. So what we will do here is we feed this to a ADC. Get the digital output, then feed it to a controller. And here we implement digital footprints. So what it will do, it will filter out all the digital noise, very high order filters are included. Then we have a DAC. This DAC will output will generate one. This is my final output. So you have what you have done. You have done two-stage filters. Okay. So basically one is an analog filter plus digital. This is how we modify the architecture so that it will work. Again, coming back. So I hope this is clear. So based on this, we make the modified architectures and we try to design our circuits. Now going next, so fine, we are making this. Then we will try to understand what are the basic problems uh, associated with these things. For that, first we will have to understand what are the different fabrication steps associated and what do you do with this. Okay. So here if you see, this is again the example of, I'm taking the example of pressure sensor only. What is happening here? Pressure sensor, as we have discussed here, we also saw on the animation.
Hello, sir. Can we have a break of 5 to 7 minutes so that the audience can have some water or something and you as well?
Fine.
Okay, sir. So let us meet at 4:11. We'll restart. Thank you so much. Yes, everyone. Welcome back to the session. Sir, may I request you to continue, please? Am I audible?
Yes, yes, yes.
Thank you, sir. Continue,
Okay.
sir. So, audience, if you have any questions, please feel free to ask. Type in the chat box if it can be useful to your research or something. We have the experts. They are ready to answer for any kind of query related to the topics or whatever devices are shown. Thank you.
Fine. So, till now we were just seeing the MEMS devices. Now we will see that how exactly they are fabricated, and so what are the typical issues associated with such things. So the case study is taken of a pressure sensor, as we have seen earlier, that it is basically a structure with a cavity, and based on the type of reference, it is defined into different classes. To be very simplify the thing, it is more or less like this. If I have a pressure sensor, it could be absolute, or it could be differential, it could be gauge. Okay. Now we're targeting absolute only. This is our case. So what we have done here, we have taken a silicon, then deposited a oxide and a nitride for the expression point of view. Then through LPCVD, we have done a poly deposition, then went for a diffusion, which is not shown here. I hope it is mentioned here. There's LPCVD polylization, and then RIE implantation. Implantation is done on the polysilicon using boron and everything, so that you can control the resistance. And after that, you do the pattern and you do the gold plating, or gold deposition or plating, whatever. And then you go for a paper bonding, Pyrex glass. So basically, seal the cavity so that it can behave as an absolute sensor. But the important thing that to observe here is that you are growing a thermal oxide of 0.6 micron, 0.6 micron. And the second thing is, these oxides, these thermally grown oxides, they are wet oxides. So let us again go back to that, because that is critical. You have an oxide which could be dry and wet. When it comes to CMOS, GIF especially, dry oxides are for CMOS plate. Wet oxides are most probably for the field oxide. Okay. But here what we have done, we have used, to be very specific, we have used a silicon when we have gone ahead with the oxide, then we have gone ahead with the poly, right? Now this oxide is wet oxide, remember that. That will be, you will see the impact of that in the later on. Now, we know very well that this oxide is having different type of charges, right? 4 types of charges are there. And these charges, they basically influence, and this oxide is having a charge. This charge influences your threshold voltage, VTH. Fine. But what about if this charge is there? What is the impact of this on a MEMS sensor? It's nothing. We are not having any problem here. So the point here is, conclusion is, oxide charge has no impact. This is very important. Okay. Now if we again go back to here, you can see here that you are making a bulk micro machining of silicon from the back side. Right? Why you have done that? You have done that so that you can make this cavity. And why you need this cavity? Because then only there will be deflection. So again, to understand what we have done, we have made a diaphragm something like this. Okay. Then we have it anchored here, this manner. Then we are applying a pressure, right? So the assumption is that I will have deflection something like this. Agree? Yes? Now to have this deflection, that's why you have done this, the statement is written. Now to have this deflection, you need to remove this entire area, right? So this entire area has to be removed. This has to be removed from silicon, right? That means initially it was something like this. Then you did some process by which you remove this entire area, and now you are left with this much. Isn't it? So this, so we have removed this area so that this structure can bend. When you apply a pressure, this structure can bend, right? Like this. But to do that, what you need to do? You need to etch out this area. Remove this area means you have to do etching. How do you do etching? You have options like wet or dry. Right? When you are doing a wet etching, you are using some chemicals like TMH and all these things. When you are doing a dry etching, you are using more or less some sort of chlorine-based reactions so that it will react with silicon and it will etch it out. But remember, when you do this, what is the impact on the top set? I hope it is clear. How do we do this? In order to do that, what we usually do, we follow this sort of process. We take the silicon, coat it front side, then go for backside etching. After it is done, then you remove front side coat. Right? But this is good. This step is good for MEMS. The question is it good for CMOS? No. That is what is the problem. That means when we are doing these processes, and these processes are required to make a MEMS structure. But this process are not that suitable for CMOS. Now what exactly in CMOS process we take? So to understand that, we will come to this later, this slide. So, come to this. Now we are slowly moving towards CMOS, okay? So please try to understand this transition properly. So this is the CMOS process. So spin well. There is I hope you understand this. Just I'm trying to revisit the well technology. Okay? In CMOS, we have single well, twin well, and three well. And this is 350 nanometer, up to 350. Sorry. This is usually 180, 110. This is usually the rest lower technology. So what is happening here? It is happening something like this, that if you have a silicon and you are trying to make a NMOS, you know very well that the substrate is always p-type, right? And it is always so if you have a bulk contact, then you have a gate, and this is your silicon poly. Okay. And these are your isolation pads. So the picture is clear. And then you go for a metallization. This is your field oxides. And this is your basically a type of isolating oxide. Picture is also. Let us say make gas here. Then you go for a value. In this way, you go for a P plus. Plus. Same thing, this is poly. So basically what have you done? You have made an NMOS here and you have made a PMOS here. But remember, this is a single well technology. This is single. And if you have two wells, that is your dual well. Similarly, you will have a complete in a three well. Okay. We will restrict our discussion to these two only because the third option is not relevant in this case. We will discuss these two only. This is not that relevant. In this case, if you see a twin well technology, as we have drawn here, what is happening? You have an N well and you have a P well. And this is the device cross section. This is the technology of the actual 100 nanometer CMOS device. Okay. So if you see it, there are total number of steps at 65. Whereas in the case of the MEMS device, your number of process mass and process steps are not more than 5, usually 5, 4 to 5, the assumption. Taking everything from the pressure sensor model. But if you are making some other initial grade sensors, it will be more. Similarly, if you see Obviously, a number of wells have been. Most important is gate oxide thickness is just 3 nanometers and pad oxide thickness is 50 nanometers. Now remember, what was the previous value? Remember that in the case of here, your gate oxide thickness is SiO2 is 6 micron, 0.6 micron, which is a huge value. So the point is, if I make a small table sort of thing, gate oxide in case of MEMS and in case of CMOS, let us say. Let us say gate oxide is 0.6 micrometer, right? Whereas, just a minute. Oh, 0.6 micrometer, and in the case of CMOS, it is 3 nanometer. Excuse me, just a minute, I need to take this. राहुल कुछ हाँ नमस्कार ये सो हाँ एक बार आ जाओ आगे होना चाहिए ये होना चाहिए सर हाँ हाँ बात हुआ बोला है ट्राई तो कर रहा है उसका सॉफ्टवेयर में कुछ प्रॉब्लम वो सॉफ्टवेयर एकदम ठीक करें ठीक हाँ so if you see here it is 0.6 micrometer and 3 nanometer. So this is a huge problem. This is a huge problem. Now if we stick to this only, see both are basically, this is 0.3 nanometer, this is your gate oxide. And this is the isolation oxide between poly and silicon. Okay. Now let us assume that I want to put both the things in a single wafer. I cannot, because of the requirement of this. Because of 3 nanometer and 0.6 micrometer, we cannot put on a same wafer, but in a single step I cannot make it. Second thing is, this is dry and this is wet. If you can also give an argument that what if I make it dry? It will take a lot of time. No point in it. You're making this is also very difficult. And if I go with, let us say, some sort of RTA process, it's difficult to achieve this sort of values. So this is the first limiting factor before I try to put both of them on a single wafer. But how we will see later, not very difficult. First of this understand. Second thing is our well depth. And whatever the wells we have, the depth is not more than 1 micrometer. And the third, the most important is in here we have processes like 1000 degrees centigrade. Now how that is also very critical. Let's try to understand. If my temperature is, let us say, 1000. Let us assume you are trying to make a sort of cantilever-based biosensor. Right. When you are making a biosensor, what is that you are trying to do? You are trying to make an anchor point, and then you are trying to put some piezoresistors here, and you will try to put some biosensor here. And due to the deflection, this resistance is some RNA soda. So due to this, the resistance will change, which we are trying to fix. Okay. What is the problem? Problem is this structure. If this structure experience to this temperature, simply you are destroying its structural integrity. So we cannot experience such high temperatures. So the temperature is also a big problem. That means you have to, the point is, you need to sequence these processes in such a manner that we can avoid these things. Gate oxide related issues, temperature related issues. Similarly, the implantation depth related issues and gate quality oxide related issues. But problem with it, all the things is, as we see here, this is valid for 100 nanometers, right? But what if some hypothetically we go to the older technologies? How? In order to explain that, my scaling says that what about my scaling? My scaling says that if I'm trying to reduce my voltage, okay, then I have to reduce my threshold voltages. That means you are reducing your gate oxide thickness, right? But if I go to older technologies where voltages are high, okay, my threshold also will be high. But my oxide thickness also will be high. So this can be used to ideally candidate, and we may have a fitting there. Best case example is 350 nanometers in hospital. Good part with this is it is single well. If it is single well, what is the meaning of it? In a twin well process, you have 65 number of steps. In a CMOS 350 nanometer, it is not more than 35, 40 steps. So we have saved many steps. And the second thing is, in 350 nanometer, the single well supply voltages are optional. I can have a supply voltage of 3.3 volt and 5 volt. And under special request, I can go up to 20 volt also, gate voltage. I can have a VDS option of up to 110 volt. So if we go ahead with such things, then there is a possibility of integrating. Now we can use these devices, but still there are certain limitations. And we cannot simply put the process, when we use a CMOS process, into MEMS process. The reason is, in a CMOS process, the majority of the device depth is not more than 1 micron. Whereas in case of a MEMS, in some cases, we are talking of surface to surface etching also. So that in that case, the same process cannot be used. So that leads to thinking that what are the other things that we can do. Right? That gives you the concept that can I make some sort of sensors which can be integrated at CMOS level. Okay. Now, when I say that statement, it is not it is true, but it has certain limitations. In order to understand that, let us first try to see that what type of sensors we are looking for. And can I say that I can actually make any type of sensor in CMOS? Are we trying to say that? It may not be so. You will see that what are the limitations and when exactly it is going to fit. Okay. So to start with, we will use more or less a type of temperature sensor only. We will not go beyond that because that will be difficult to explain in this winter time. So let us assume that I'm taking care of the temperature sensor. Okay. Now when I say a temperature sensor, you must be knowing that what are the different technologies available in temperature sensor. So we can have a sort of RTD. We can have a sort of thermistor also and thermocouple. Now all these things can be used. But what is happening here exactly? They are all basically a type of resistance only. I mean, we are using different type of combination of metals. It's nothing more than that. But if I take a RTD, let us say I take a RTD is nothing but a resistance. We are trying to capture the resistance only. So we are taking the resistor and then let us assume that we are putting a current sink here. We are trying to sample the voltage here. And obviously it has dependency with temperature. And we know very well that it has very wide temperature operating temperature range, like roughly, I believe, 800 right? This is a very good temperature range. And in this, we can say that it will work. But remember, again, if we go back to our previous discussion, this is a resistor, it is a metal resistor. So it will again generate noise. And this is sitting outside your design. So if this is my circuit, it is sitting outside. I cannot simply integrate this in my chip. No, it doesn't work like that. Right? So that tells me that what type of circuits I can have by which I can integrate on a single chip, but still it will work. Now, if we see on a chip, what are the things available? In the CMOS technology, if we see, I have R, C, MOSFETs and diodes. We can measure with these are the things that are available. Now, typically, I am giving you two examples. Like R can be used as a temperature sensor, that we have seen. A MOS capacitor can be an image sensor, basically the case of the system. Diodes can be used as a temperature sensor and for telling of a simple diode, PM diode. Diode can be used as an optical sensor also. I'm taking out the pin transistors. MOSFET as temperature sensor obviously because they have temperature threshold is dependent on temperature. You can operate that. MOSFET as image sensors, obviously CMOS cameras are also. Modified MOSFET can be used as a biosensor. More or less we are telling of these sort of things. So if we see here, now again we will come to resistors only because that is where our discussion lies around. How will you implement resistors? See, the resistors can be based on, as we have discussed earlier, to be metal, N diffusion, P diffusion, N well, N poly, P poly, and silicon. So these are different process technologies that are available to make a resistor. But all of them have different behavior. Okay, normalized resistance values if we see. This is a typical characteristics class. And if we see from the thermal point of view also, this is the typical equation, and this is having the second order dependence. That means we need to put all these coefficients, then only it will work. Consider the example of this simple circuit. And here what is happening? Let us say I have a on-chip resistor. Now I have taken this like this, that I have taken a on-chip resistor like polyphonic resistor. Then I have put a IDF resistor to this. And then I am trying to feed it to a ADC. So if there is any variation here, okay, so what will happen? Basically, any variation at this point means your voltage will change here. That voltage will be converted using the ADC to a digital. Okay. Now,
Sir, we are not able to hear you. Hello?
yeah. Now it is fine.
Yes, sir. Now it is. Yeah.
So in this case, if you see this is a this is used as a temperature sensor. This is my physical resistor. This is potential resistor. In this case, you are using, let us say, a SAR ADC.
So, sir, I have a question here. This ADC means this can be taken up from the market, or we need to design at our own?
See, when we are telling of CMOS sensors, it is better to make a own ADC. Then only the performance will come.
Okay. Otherwise, it will be costly because different type of packaging and cost from the market is also increased, right?
It is not exactly like that.
Okay.
I will explain you a little bit here. Let me explain
Oh, okay, sir. Thank you
why.
so much.
And it also depends on the type of architecture also. It's not like that. Let us say that we have gone ahead with uh, let us say SAR ADC. In SAR ADC, as we know that what is the architecture? The architecture is I have a sample and hold. Then after sample and hold, you have a comparator. Comparator output is that is getting fed to a SAR logic. This is generating my digital bits, getting fed to a DSC. And this DSC is generating my another voltage. This is my digital output. And this is my very basic architecture. Nowadays, nobody uses this. They go ahead with a merged architecture. The margin level is so high that you actually make all these into a single block. It is a single block. Yeah. It's not going to that. Let's understand the issue. Problem here is, how will you implement this sample and hold? When you see a sample and hold, what is it? If I am going ahead with a flip around architecture, let us say, the flip around because of its better feedback center. So you have a cap here, you have an op amp here.
Sir, are you speaking something? It is not audible.
No, I'm just drawing it.
Okay, okay.
Yeah. So if you see here, what is happening is basically there are two cycles. In the first cycle, the cycle 1, this is happening, right? So here what have you done? You have done the sampling. And in the cycle 2, you have taken this. This is your cycle 2. Right? So if you do this, to achieve this, what have you done? This is shorted. This is shorted. And this is shorted. So this will be a capsule. So this will be a capsule. So this will not. Now it's fine. Fine. So these are the two cases. Now remember that you are using the same capsule. The same cap is getting the two position to that. That's why your feedback factor will be very high. It will be nearly equal to 1. You are not using additional switches. Otherwise, you need more 2 caps actually. You use 2 caps. But the problem here is when you are using a configuration something like this. Okay. Then let us say that this is the above configuration, right? In this is nothing but a transistor, right? So when you are trying to switch it off, whatever the channel charge is there, what about the channel charge? That will always go towards the whatever the impedance is, right? So it has a tendency to distribute among themselves. When it happens, what will happen? A few amount of charge will get injected into this section. Now remember, this node is connected directly to this. When you have such a scenario, that means any disturbance here is directly getting injected into VDD or ground. Okay? Now, in order to control that, what we usually do, we try to put some sort of dummy caps here. Deliberately, we put some dummy caps in this part. And that ensures that whatever this additional charge is there, that is getting absorbed by this charge, by this dummy cap, to ensure that minimum feed through is happening in this direction, so that my sensor is not getting disturbed. Fine. Now, hypothetically, if I am going ahead with a scenario where I am taking a, let us say, a commercial ADC. In a commercial ADC, what is happening? You have ADC code. This ADC code input is fed to a IO driver, IO pad driver. This IO pad is connected to a wire bond. This IO wire bond is connected to a package. And here you are getting connected with your sensor. This is the sensor, this part. Right? So even if there is some sort of injection is there, I mean there is some charge injection is there, there is no way to suppress those variations here. We cannot do anything. The second thing is, when I have such a large part, so whatever the voltages I am generating here, they are already of the order of, as we had discussed previously, my sensor output is not in the terms of volts. It is of the order of few millivolts. So these millivolts, when they travel through all these paths, where we are targeting a sensitivity of, let us say, 1 millivolt, you are already losing more than 80% of the voltage. Yeah. Change in voltage. So putting a sensor outside and then connecting directly through the ADC is not a good option. It has to be, that's why this should be on the chip itself. And on the chip, you need to put these sort of caps, or you need to put some sort of decoupling caps so that your noise levels are less. Or you choose some sort of architecture where this noise is not there. Like if I go ahead with, instead of, let us say, I will take, like I have SAR, flash, and pipeline, let us say. It is not good to go ahead with SAR and pipeline. It is better to go ahead with flash. But somebody can give a counter argument that if I go ahead with flash, my resolution is limited, right? But that we can't do anything. So that's why it is important that what architecture you are choosing, whether it is continuous time or switched. And the third thing is where exactly your sensor is connected. If it is outside, not at all good. Am I clear? Hello? Hello? Am I audible? Hello? Am I audible? Okay, okay, fine. So we will move ahead. I hope you have understood the point. So with this, it is clear. With this, it is clear that if I have something like this, with this configuration, I can use a on-chip register as a temperature sensor. Okay. Now, will it? How good it is as compared to a traditional, let us say, a voltage, a temperature sensor? It is definitely better as compared to a off-the-shelf temperature sensor. But there are certain limitations with this sort of uses. That can be like this, that we have already discussed about it. Again, I am trying to tell you. We just imagine how have you implemented this register? Okay. See, this is, as we have discussed, this could be diffusion or this could be poly. Well, let us come to diffusion first. So let us say I have a substrate something like this, and I have a diffusion something like this. This is P type, and obviously this is N plus P type, because you need this space type. And we are tapping these two voltages, let us see. Okay. Now, if you are applying different voltages, let us say hypothetically, I have something like this is VA, and this is, let us say, VB. Let us say VA is more than V. What will happen? obviously you are experiencing more, this is your resistance. So this region, obviously it will change because of the higher bias, higher voltage that you have applied. That means this depletion region is a function of your voltage, and with voltage it is changing. And with voltage when it changes, that actually gives you another dimension to your voltage coefficient. So we can say when a ballpark number, it could be like this, where based on the process, your thermal coefficient can change by a value of around 0.2 to 0.1%. So that is a very big value. When you go for a very high sensing applications, this is the percentage wise, this is a very big value. So in that case, it turns out that it is not a good option to go ahead. Now this is from the diffuser resistor. This is the diffuser resistor. What about poly? In poly, if you see, I hope you must be knowing these things. There is something called as grain boundaries. So these are the grain boundaries in a poly. So what is happening is, across these grain boundaries, there is something called as a release and a trap phenomenon. Okay. So due to this, what will happen? That the whatever the carriers are there, they will get trapped and released across the grain boundaries from this statistic. It is here, it is getting trapped at this point. At some point, let us say at this point, it is getting released. Now this will have a second sort of issue. Due to this, the resistance will slowly increase and it is very unpredictable. And so this sort of thing will have a problem with respect to time. Now, due to which it turns out that we cannot use such very simplistic structures for sensing application because they are inherently having problem with the sensing mechanism itself. So, what is the conclusion is that from design point of view, it is possible. Yes, it will work. But the problem is they are non-linear. And in some cases noisy. And in some cases a drift is also there. So this is the condition of a what? Resistance on chip. It could be for diffusion or it could be for. Fine. So we can see that this problem is there. Now let us go to the next type of sensors that we have studied here. That is the category. That is the image sensor. Image sensor you must be knowing. You must have used cameras. And in cameras, the mobiles are usually CMOS sensors. But if you see the professional cameras, they are majorly CCD based. CCD is nothing but charge control devices. They are nothing but MOS capacitors. So nothing more than that. So if you see what exactly is that? Yes. What is their architecture? Hope it is visible, right? this is the case, and we have taken a theta, obviously, 100. This is a value. On top of that, we have made a N channel. Okay. On top of that, we have made a silicon dioxide. The barrier, basically this is the barrier. On top of that, you have made a polysilicon. This is your polygate, so that is not you get confused. This is polygate. This is N channel. And this is your silicon. This is your oxide. And this is your charges are getting charged. And this is your potential current. You must have read semester coursework. Okay. These are basically the generated electrons. Okay, obviously you need to bias this, otherwise it will not work. And you are having the photons. You like basically these products, nothing. Obviously you need to bias this also. Cannot be minus and plus. Fine. So this is basically nothing but a MOS capacitor. And this is there in the CMOS process. This is not available just like that, but these are the CMOS compatible processes are there. You will see that later on. But these can be there, and you can make error of it to identify the image sensors. Now, if you see this, what is it more or less like? If I see the analogy sort of, probably the best analogy for this is the water bucket analogy. What point is, how do they explain that? It is like this. But let us say that I have something like this. I have some water buckets like this. And I have kept them at a certain height, let us say. Okay. And I have connected them. There is a pipe which is here. And I have another bucket here, let us say. Okay. And they are obviously sitting on better height, and they are sitting like the lower down. And then what we have done, we have connected them in this manner, connected a joint, and I have collected the water. The final top is status. So if there is some, let us say there is a rain is falling on it. So let us say it is getting filtered by some margin. So what will happen? As they are connected, the tendency of the water will flow here. The tendency of the water will flow here. It will fill it up. Similarly, it will flow here and fill it up. Similarly, it will flow here and fill it up. Now, once it is filled up, all of them, they will flow through this, right? Agreed? And they will get connected. Right? This is a very good example of exactly how a CCD works. So if you convert this analogy into, let us say, circuit, what is happening? Basically, you replace all these buckets with, let us say, how will I do this? replace buckets with, okay. So if I replace this with caps, what will happen? So you have basically a charge that is getting added, and then you have a sort of row recorders, and then I have a column recorder. We will see that how the charge will be. Then what I will do, I will try to have a sort of ABC here. And this I'm trying to get the output. Okay. So what is happening? This is a multi-channel ABC basically. So with this I can convert that. But the point here is, if we see here, now that is the circuit part basically. But if you see the device part, this I can, hello,
Yes.
hello, yes, yeah, anything, any doubt or anything? Hello, any question or anything, or should I continue? Fine. So if you see here, what is happening? This is more or less like a capsule. So what type of architecture you will be having to basically
Hello.
what is, hello,
Sir, can you hear me?
yeah,
Hello.
hello, yeah, yeah, yeah,
Sir, we can have a 5 minutes break if I
oh,
think that
fine,
would be better.
fine, fine.
Yes, sir. Yes.
So,
Thanks.
without. So we will discuss the mass capacitor, but first the thing that we have discussed regarding the temperature sensor, we will see that how exactly the temperature sensor plays an important role in CMOS chip. So sir will explain from the SOC point of view. Okay. So the point is, if I am using a temperature sensor in acid, and if as an example is my SOC, how exactly it will work? So that we will see. Yes.
So when we see any kind of SOC, it will consist of a processor. There will be a processor, microprocessor or microcontroller, and there will be bus and some peripherals, processor, coprocessor, and some memory element also. Okay, and some secure boot code is also there. Secure boot code is there. Now this SOC, it can be a system on a chip. This can be used in for any purpose, like for the security of any big device, or it can be for our mobile also. Mobile uses a secure boot code in the form of firmware, and it lies on a motherboard of that, and the complete system is a SOC kind of thing. Now, to prevent the functionality and intended operation of this, and also for the reliability, there will be some sensors which can measure temperature. Like when we charge our mobile phone, other it senses that okay, temperature is large, so it won't charge our phone. So the sensor can be of many types. It can be of diode connected, can be diode connected sensor. It may be a oscillator, thermal oscillator or ring oscillator. You can say ring oscillator, or it can be a digital sensor also. We can also write some code in our microprocessor to sense the temperature via these sensors. So when, as and when the temperature reaches at that point, it will shut down the operation of computation, sensing, and communication. Another use is suppose some unauthorized person wish to tap the system or our chip, and as and when it puts the probe and temperature rises, it automatically resets the operation and the complete system will be shut down. So the nature of the sensing varies depend upon the sensor requirements. So here diode connected sensor can be used on chip. On chip, when we say it is a complete associated with complete on a single chip. It can be in the form of 5 mm cross 5 mm. The size can be of this 5 mm, 5 mm, and it lies complete thing. A microprocessor, peripheral, and communication bus. Communication can be in the form of I2C, SPI, and other things. And at the this side, sensors will be connected in the form of diode connector or ring oscillator or digital. So they will prevent the operation of the complete system for enhancing reliability, for making the system secure, and also most importantly the boot code will be preserved. Otherwise it can be corrupted if we are not going to monitor temperature or other ambient environment through connected sensors. We can have many sensors in advanced forms, but now we restrict ourselves as the course motivation is to have diode connected and some basic sensors. So we are stuck with this. So System on a chip design can be of many types. It can, and it is also at the bottom level process oriented. So in our system, when we write code in microprocessor and connect this complete system to on chip buses, and later on when we design it at the bottom level backend. So at the layout level, we can also form some sensors and other things, and also we can import third-party system or sensor in our SoC environment. So it allows to have third-party black box. It is also known as a macro or some IP cores in the form of uh, uh, it can be of GDS2 form metallization layer, and we can import this GDS2 at the physical design level. And our suppose this is our chip, SoC chip, and SoC plus this GD2 in the physical form, both can be connected and it will be processed, and now it will be a system on chip with embedded on chip sensors for reliability, for security, and for proper operation of the intended system. Yeah. So please, if you have any question related to this, you can ask. Otherwise, we are moving towards some other operations for differential and other. As we are discussing this with ADC and its implementation, we'll move ahead.
So, coming back to the CCDs, as we have seen here, basically this is, we can say in this analogy, we use ADCs, and through ADC you try to convert the charge into voltage sort of. It's basically a sort of the voltage converter circuit. Now, as I was saying about SOC, you must I have to have understood that it turns out that I cannot put a RTD in a asset. It's not possible like that. Right? It has to be a CMOS sensor. Otherwise, you cannot integrate on the chip. So it turns out that there is a very specific requirement of CMOS sensors, though they have limitations. But if used properly, but there is a limitation that you cannot put too many sensors also, because each sensor requires its own interface circuit, digitization circuit, calibration circuits. So it should be there is an optimal number that, like in any chip, usually not more than 3 to 4 temperature sensors. Otherwise, it is not possible. Similarly, on a single chip, you should not have more than 2 reference circuits, because that itself will consume a lot of petrol, and so there is no point to put more designs. So considering these facts, if we see to the next thing, diode is a temperature sensor. Now see, temperature sensor, I can use a diode as a temperature sensor also. So why, how can you use it? As you know, that any diode, let us say I take a diode. What is the equation of diode? I hope you know all these things. I'm just reiterating this. Right? So this is the equation, right? The point is, I know very well that this is dependent on temperature. Hmm? So in return, this actually controls my current. Hmm? So if we see the characteristics of this, it turns out that my current is basically changing in this manner. If you do the plot like this, my diagram is not that good, but if you see that with the increase in temperature, what is happening? We're actually shifting towards this direction. This is the increase in temperature. This is your current, and this is your water solution. Okay. So I can use this behavior as a temperature sensor also, which people have done, like uh, they have done two basic circuits where it can be used. Like let us assume that I'm trying to use like this. I have a current source, and then I'm trying to use a diode in this configuration. So based on temperature, obviously its current will change, and that will be used as a threshold to a differential amplifier. Uh, so it will generate a pulsed output. Okay. I can use such basic circuits to monitor my temperature, and these things are widely available also. But the problem is linearity of the diode. So this could be in this manner also you can use a diode as a CMOS sensor. Third thing is diode as an optical sensor. This you must be knowing that there is a configuration called as so whenever there is a photon is there, so your current will change, and that actually you try to detect it through a circuit, and it works. But if you see, but among them, from the linearity point of view, if you try to understand, these circuits will not work properly because of their inherent nonlinearity. So the best circuit for this is MOS. It is better to use MOS as a, so as per our whatever we have done, if I want to use it as a temperature sensor, the best case scenario for them is either you take a poly resistor, or if you don't have, you take a diffusion resistor, or you take MOSFET. Diodes, no, they have certain limitations. They can be used in reference circuits. But as a temperature sensor, if you see, they have certain issues because of the nonlinear behavior. To understand that, let us say, you take the case of a transistor, something like this, let us say, I make this configuration here. Is it visible whatever I'm trying to draw? Hello. Let us say I have a current source something like this, and I'm trying to, and I have applied a bias voltage here. So, and I'm trying to operate this, and let us say linearly. What will happen? Any guess? Fine. So that if we see some equation wise, let us say in linear and in substrate properties, we will see that very interesting behavior is there. We know very well that ID sub is nothing but IO yes VDS, right? This is is a very standard equation. There is nothing. But we know very well that Vt is having temperature dependency, which is nothing but agreed? This is the process temperature. Okay? Not going into the detail. But we also know that Vt is nothing but phi ms. This is again very standard equation. Fine. What is the meaning of this? The meaning is, if we put all these equations and see, it turns out that if I can control this behavior, if I can control this behavior properly and tune it properly, I can have a dependency something like this. If you solve these equations, you will find out that we can have a dependency something like this. Okay. What is the meaning of it? The meaning is, if I can tune the mobility terms properly, because knowing very well that my mobility is a function of, what is it? How exactly mobility varies? So keeping this into value, I can tune these parameters and I can have the characteristics which can be used as a linear temperature sensor. If you do the plot, you should have something like this. This is basically the case of a linear, but this will work only when you have done the VGS plot. But if you see here, this is having a very linear behavior, whereas in case of a diode, it is not that linear. What you have to do here in this case, you have to design this circuit very carefully. And this is more or less keeping the diode in a suitable operating point so that it works. Otherwise, it will not work. So, designing of this current source is a very critical role here. So that limitation we can eliminate if we are using a MOS as a temperature sensor. Fine. So this is MOS as, I'm only talking of temperature sensor because there only we can compute everything. Now just to give a specific idea, so MOSFET as a biosensor because that has a lot of interest. So what is happening here? So I hope this is clear up to this point. So the conclusion here is MOS is a good temperature sensor. There are certain conditions, but if they are fulfilled, it is a good temperature sensor. Now coming to MOS as biosensor. This also has been demonstrated on a single chip by researchers. Now, what have they done is, you know very well that a MOS, let us say, draw like this, and this is my gate oxide, right? This is my poly. I'm not going into that. Okay. And what is happening if you are trying to ground this one, and this is also grounded, and there is this is at a higher potential, this is also at a higher potential, and this is not efficient. What if I can remove this gate, and this is a standard one, right? What if we do something like this, that I have this, I have a source, I have a drain, I have a gate, then what I do, I put some sensing layer here, some sensing layer. I made a mistake. So this, if I put a sensing layer, let us say this is my oxide, and I am putting a sensing layer on top of that here. Okay? And then I make a cavity sort of thing, let us say like this. Okay? And my biosample is, let us say, and what is happening is, we know very well that this oxide has charges, right? This oxide has charges. This has charges. So due to this will react with this sensing layer, and it will alter the threshold voltages so that the current conducting through the channel is altered. Okay, so in that case, what will happen? In that case, based on, when actually I am sensing my biosample, this is my biosample. And this is my MOSFET. So the concept of FET and all these things, and this FET is this one. Structure can be different, but more or less it works on the same principle. So what you do here, you take a transistor. So what you do here, you take a transistor, something like this. You have a gate, you don't apply a voltage. You put a current source so that you can generate the voltage. Then you apply some sort of biosample, and based on which you will have a voltage. And these two relations, the biosample concentration and this voltage, these two will give you characteristics graph. And based on, so this is also working like a sensor. This is also a circuit which is widely used nowadays. So to make it as a point of view, in the biosample point of view. What is the point of the, what is the basic observation? Basic observation here is that I have a circuit, and I'm using this circuit to detect my sensor out, and that sensor output I am trying to digitize, and based on that we are trying to generate the direct correlation between sensor output and my actual output. But all of them has to be on a single chip. how will you do that? If it is MOS compatible, now in this, then we will go for the classification because it is not that simple now. I have a circuit, I have a sensor. Now this sensor can be CMOS or MEMS. Now in this CMOS also, it is with PDK or it is third party PDK. PDK is nothing but process design. Now things are simple if this is this flow. If this is the flow, then what are the sensors that you can make? Like the systems that you can make? You can make poly or diffusion based plus chip that will give rise to a temperature sensing system. Fine. Let us say you are using a third party PDK sensor. You are using sensor CMOS and third party PDK levels. Then what is happening? You have CCD or CMOS or photodetectors plus chip that is giving rise to your camera, majorly camera you can see. Okay. But remember, this is both of them. Both the things are on chip, on a single chip, but this is having no area, no boundary, no separate boundary, no separate. But this is having actually a separate boundary. Please try to understand. I am trying to tell many things here. If you have any doubt, you can ask, otherwise difficult to understand. So, what do you mean by this? I will explain. Third case is, I have a sensor, it is MEMS based, and I have a circuit, and they are on a single entity. Single entity means this is again two types. Two chips, two separate chips, or monolith. Okay. So when you say two separate chips, this is nothing but it could be SIP, it could be LTCC. Okay. Whereas this is on a single chip. Now we have actually, if you see, there are so many things. This is also separate boundary. If you say this is also separate boundary. This is completely two separate things. So I can say from the whatever we have discussed till now, there are typically four classes: class 1, class 2, This is class 2, class 3, and class 4. So there are 4 classes for sensors with circuit. Now these 4 classes basically make the entire spectrum of our elements. Okay. And whatever sensor you see nowadays, they are any of the 4 classes. It cannot be anything apart from that. We have covered almost every aspect of that. Now the question is, what do I mean by that? When I say that these are my 4 classes, what do I mean by that? So I'm not going more into circuits because that is itself a different domain. When designing chips, when designing custom circuits will require a separate tutorial itself. But what I'm trying to say here is, you see, we have reasonably covered the temperature sensor to greater detail. Let us not go into those type of details for other sensors. Keeping that in background, let us try to understand. Here I have said there is no separate, here I have said no separate, right, for CAT class 1. What is the meaning of it? Meaning is, if you see a chip, any ASIC, what is that? You have a core area is there. This we call it the core area. Then we have a pad area. This is called as the pad plane. My diagrams are not good. Please bear it. So this is your pad. Then comes your package. This is your package. Right? And on package you have these pins. Right? Now concentrate on this core area. What do we mean by that? Let us concentrate on this. In this, if you see what is happening here, there is one package, one chip, only one chip is there. Okay. And in this one chip, if I say, if this is my chip area, somewhere here my sensor is there. And my entire circuit is all over here. If there is no separate, because it is also compatible with the same process, during the same process, you are also making the chip plus sensor. What is the meaning of it? Simultaneous fabrication of sensor plus chip. Okay. That means if I see the planar point of view, let us say, it is obviously understood that if I am taking, let us say, a MOS based temperature sensor, so at the same step, my oxide is getting formed. We have discussed, right, the previous, that there are 60 odd steps are there. Here I believe we have discussed that. Here we have discussed there are 65 steps, right? That means in those 65 steps, you are making all the sensors and circuits, no separate step. I hope it's clear. Now let us come to the case of this category 2. Right? In this, what is happening? You will have a clear demarcation. Like if you are making, let us say, I am making a CCD. So this is my CCD area. And after that, you will have a clear cut rings around this CCD. And then you will have your chip here. This is your chip. And this is your CCD. Okay. So what is happening in some cases, you are going for a post-process based fabrication. So what you do, you make the chip first, and it could be any way. It could be any way. Like in some cases, select chip first, then you make CCD. Okay, but they are sitting on the same chip. But the point is, they are sitting on the same chip. This is called the post-fabrication. So the same concept there also. Then comes the case of SIP. Okay. In this, what is happening? That what we usually do in India is we make a chip, then we make a sensor, and then we say these are two separate chips, dies, die 1, die 2. Then we put it on a single package. On a single package, you put them, and then do whatever wire bonding or whatever it is. And you design. Now there is no dependency on process or anything because this is package level wire bonding is going on, so it doesn't matter much. Now the third case is where it is a monolithic. See, monolithic integration is happening in two cases. In this, it is also pure monolithic. This is pure monolithic. This is pure monolithic. This is also pure monolithic. Single chip. Okay. So here what is happening? I will take the example of, let us say, a pressure sensor, again pressure sensor, because that is the best case scenario. In a pressure sensor, as we have discussed, what is there? If you take this, you have a oxide, then you have polyresistors, and then you have metallization on top of that. Right? This is happening. Then you have a cavity and you are trying to apply pressure here. This is the difference. So what are the things available here? What I need oxide, I need poly, I need metal. In a CMOS process, this is the MEMS This is the mix. In a CMOS process, I have oxide, I have poly, and I have metal. We have discussed all these things previously. I am not repeating them. The problem is only this, oxide thickness and poly diameter. If we can somehow find a way to accommodate both of them, then my problem is done. I can make this monolithic is possible. Right? This is possible. So how will you make it? To do that, there is something called as co-fabrication. Okay, this is called as co-fabrication. Do you need a break? Hello? Do you need a break? Or should I continue? Okay. So if I see the co-fabrication, what is happening here? I am trying to do the process simultaneously, but I will do it in a very judicious way. Like, hypothetically, let us say this is my silicon, and I have defined a specific area, let us say this area. This is for sensor, and this is for CMOS. Okay? It's for sensor. First step, I am trying to do a diffusion process. I will go for a simple oxidation. Let us say simple oxidation. I will go ahead with a gate oxidation. Go ahead with a gate oxidation. Now, gate oxidation, as I discussed earlier, that it is same. Both are like this. Then I am going for a source and drain ratio. Now, in this, I will try to do some sort of masking. And I have done the source and drain. If that is the case, then I go for a, this is done, then I selectively etch it out, the oxide. Okay. I'm not, it looks like I will do this one. Let us say we keep this oxide only, and then we go for a poly deposition. Let us say. And when I'm doing poly deposition, I'm also depositing here also. Somehow I remove this. Okay. So I have done the poly deposition. So what are the steps that I have done simultaneously? One is gate oxide. Second is poly. Right? So when I do this and this, I have defined my, what I have defined my polyresistors, gate. Then I go for, let us say, next step is metallization. So I remove these oxides. These oxides are removed, let us say. And then I deposit some metal here. And I deposit some metal here also. And this is the rest of this is the metal. Okay. So what has happened? I have done metallization simultaneously. These three processes are in sync. But when I go for the third process, the fourth process, that is nothing but the backside etching. Let us say I go for ahead with the backside etching. Okay? Backside. Somehow I try to cover this with this. And then go for a backside edge. And open this with this. Then what has happened? You have created this cavity. Now what is this? You see the top view. From the top view it is clear. So this is my total chip. This is my sensor area. And this is my assay. They are actually connected to the metals, chip metals. And this is my single chip. And we have integrated everything on a single die. But remember, the sensor area is clearly demarcated from the assay area. Right? And it is actually, there are certain ARC rules also are there, which need to be ensured when you do this sort of process, so that you are not creating any issue at the asset level. Okay. So we will see one small case study. We will not go into the details because that itself is a different thing. So here what have you seen? Here we have seen that two distinct areas are there, but they are on a single chip, right? If you come back to this, it is monolithic, single chip, but it is not completely merged like the case of grade, in the category 1. So I give this as cat 1, cat 2, cat 3, and cat 4. I can say that every category is distinct in itself. Right? It is not that you can have a same solution for everything. No, it doesn't work. Everything is distinct in itself. And type of sensors that you can integrate on a single chip is also depends on the type of accuracy and the type of form factor you are looking for. It may happen that in some cases you can do both category 1 and 3, both 1 and 3. But it depends on that application, what is the application required. Okay. Like I can give you one example. That let us say that I am trying to integrate a type of temperature sensor only. I will go back to temperature sensor. One temperature sensor could be a mass as a temperature sensor. The other temperature sensor could, if I am making a polyregister, but the polyregister is divided into series and parallel combination using the MEMS type of polyregisters. The benefit with that is whatever the non-linearities associated with the polyregister that we have not discussed, that can be mitigated by a series parallel combination of polyregisters. Okay. So that if we do that, then our dependency on circuit can be minimized to a great extent. To understand that, to just to give a clarity of that, I can say that, let us say, you have a circuit something like this. I'm not going into the details, I'm just giving you one small idea, that's it. Let us say you have a circuit something like this. Okay, then let's maybe. If you see its phase output with respect to temperature, to do the calculations, it turns out that you will have a slightly nonlinear like this. But this is not acceptable. When in applications, in certain applications where you need very high performance, this may not be the right solution. So in this case, this is your actual on-chip polyresistor. Instead of that, if you go ahead with something like this, let us say, this is I'm telling you a hypothetical case that I have a current mirror. The current mirror is being stacked on a two cascaded structures. Yes. So this is my VDD, and these cascaded structures are being, let us say they are being set biased externally. There is a bias circuit. Okay, and this bias circuit is generated to a voltage generator, and you are feeding this, and then you are trying to feed, let us say, you are tapping one voltage here, and in return, this is generating the bias circuit. So this will generate a voltage which is predominantly linear, let's say, a very linear output. And this is all pure CMOS based. So it turns out that not necessarily CMOS sensors are always good. No. They have certain limitations. They are good in certain cases, but we should be careful while selecting the sensors for what application we are trying to do. Similarly, there is a circuit where diode is used as a humidity sensor. Okay. So what you do, you try to take a diode, one you isolate from the environment, and the other you expose to the environment. So whenever there is humidity, what is happening? There is a change in temperature. That change in temperature with respect to humidity, they try to relate when you are taking the diode to elevated temperature. So deliberately taking the diode to elevated temperature during certain time. Then you expose it to the humidity. Then you see what is the change in temperature due to which there is a change in current. The change in current will correlate with temperature, then you will figure out. These sort of things also people have done. The point is, all these things have been explored, and there are certain boundaries, as we have discussed here. As we have discussed here, this different categories. We are exactly trying to understand that. Okay. Now taking this ahead, going this ahead, if you see here, what is the issue? If the best case scenario is category 4, right? Category 3. Although we have certain limitations, but category 3 can help us in fabricating almost all sensors. If this is possible, let us say hypothetically this is possible, I can make static sensors, static elements, okay? I can make dynamic elements, in dynamic I can make inertial wave sensors, I can make magnetic sensors, and in static I can make pressure sensing sensors, gas sensors, all these things. The point is, if this is possible, if this case is possible, then it solves all our purpose. We don't need anything else. Then everybody should have gone ahead with this, but no, there is certain limit. Okay? So that limitation we will discuss. I need some water. Uh, Moini, are you there? I need just taking a 10 minutes break. Okay, so let's start. I hope everybody is here.
Yes, sir, you can start.
So, till now, we were just seeing the issues. So it turns out that the golden case is if we can have this scenario is a golden case. Right? Our category 3, monolithic shape. In this, what is happening? In this, we are trying to fabricate both the devices simultaneously. And we have sequenced the fabrication steps in such a manner that the sensor is also getting fabricated nearby. Okay? They are sitting side by side. But is it so easy? We will try to understand that. Think of a situation like this. It's like a parasite. We'll take the example of a cell. Okay, let us take the example of this cell. This is again, this can could be amplified, assuming that both the capacitors are same. I'm considering this as the sample and hold circuit. Hmm? So what is happening in the phase 1, you are sampling across this capacitor, and in phase 2, you consider virtual ground here. So this is also this is your actual ground. This is your virtual ground. In the phase 2, what is happening? The moment you engage the switch, this charge will be pushed towards this capacitor through this virtual ground. Okay, obviously because it cannot hold the charge, you have pushed this node near to this. Now, what is happening? It is working fine. What are the limitations? If you do the layout of this, I'm not going into the timing, the switching circuit delay equations, just concentrate on the layout. For this, the assumption is my switch is ideal right now. I have considered them ideal, and I'm assuming that the noise is zero. Okay? Both external and internal. Both external and internal. Because that will make my analysis simpler and my amp is reduced. Will make our life easier. Hmm? So, if this is the case, how will you do the layout of this? Layout of this you need to do. So you need to match these two capacitors, right? These two capacitors need to be matched. Because if there is any mismatch, as we know, then nothing but this is the ratio between these two. Right? Output is ratio between. So that will give an offset. So how will you do the layout? We will do the layout in such a manner that they are in close proximity and more or less they are intertwined. So let us say this is your area where you have the measurable capacity. That's we have implemented. And then here you have implemented because in the cap, if you see, switches are there. So you have done, let us say, this is your switch matrix. Let us say this is your switch matrix. And then you have implemented your AMP code here. And then you have put some decoupling. This is your DC caps. Here you have put some DC caps to this. And you are taking the output from here. This is your output. This is your input. This fashion. Great. Now you are trying to do the co-fabrication. This is called as co-fabrication, right? This is co-fabrication. Already I have mentioned. So in co-fabrication, let us say you are trying to, you have done something called as, you have done some PR. Here, what you have done, you have put it, let us say the step is, you have done PR putting of circuit. Okay? Now, why you have done that? Because you have done that because you are trying to do the backside action. You are trying to do the backside action. Okay. If that is the case, if you are doing the backside action, so you know very well that it could be, let us say you are doing the wet action, and so your dry action you are trying to do. No, you have done the backside action to open the cavity for the MEMS sensor. After that, you want to remove the PR, right? To do the rest of the process. Remove PR. Now, when you do remove PR, it is nothing but dry edge. When you do dry edge, because remember, when you are doing backside etching, your PR coating has to be very thick. Otherwise, it will damage your circuit. Right? This is, let us write it down. Backside edge, long duration, so high PR thickness. Fine. So when you do a dry edge, the problem is you are actually putting some unwanted charge on the cap, on these caps. And then in this process also you are, I assume that you have followed all the DRC rules so that the antenna and all these things have been taken care. But you cannot avoid charging the caps. Now what is happening? Let us say that I have some residual charges here. Let us say I have a residual charge here. Then what will happen? If that is the case, my output will have erratic output, obviously, because I am not able to, it is a random effect and I am not able to discharge it. So to do that, what I have to do, I have to put an additional switch here. This is additional. In ideal cases, it is not required. But if I am trying to do such things, then I have to put this switch. Agree? This is one thing. Second thing, there could be some residual charge here also. So what I have to do? I have to introduce an additional block that ensures that this is shorted after few cycles. So what modifications I need to do? I need to change the switching sequence of this one to 1. So in the intermediate, I will generate a switching sequence with this 3 thread. The modification is block level, second, is additional switches. Agreed? This is done just to ensure that due to this additional step by H, I'm not leaving any unwanted charges across the gaps. Now just imagine that I have take the case of a ADC, where you have multiple such switches in a sample and hold circuits, or somewhere where these sort of ratiometric capacitors are used. It will be very difficult. You need to tailor-made the circuits in such a manner that they actually work in this environment. I hope it is clear. Is it fine? This is the one thing. Second thing is, if you go back to the structure, okay, here what we have done, we have deposited the same process. We have deposited a large poly structure and a small gate poly. See, the gate poly is very small. For a 350 nanometer, how much? It will be roughly around 350, right? This is the gate length, if I say. But this is of the order of some micrometers. So due to which what is happening? How would you implement this poly? Implementation. So second thing is implementation aspects. Implementation aspects means you have a process called as LPCB. That is the only process by which you can make poly can be deposited, poly deposition. Right? Now, if you do this in the LPCB, you are at one point you are making a resistor of this size, which is something around 100 micron or 200 micron sort of thing. And at some place you are making a gate which is 350 nanometer. So the problem is, once you make this, then you have to go for diffusion also. And the diffusion recipes have to be shown in such a manner, because this is very critical for photovoltaic, that it controls the sheet resistance equally for such a large structure and for such a small structure. Extremely difficult. And so when you do the when you try to generate the Monte Carlo file for this, you will see that due to this, lot of variations have occurred in this. That means your circuit design reliability has gone down. That means I means if we are trying to make, we have to be very careful because circuit reliability is poor. So to avoid such things, we go for, what is the only option? We go for complex digital calibration. This is the only option. Otherwise, you cannot ensure that actually it will work. What do you mean by that digital calibration? Again, I am giving the example of pressure sensor only because we have been in that line. A typical pressure sensor, if I take, it could be MEMS or MEMS, it has to be MEMS, pressure sensor means. This is a chain, right? But as it is on the same wafer and there are a lot of uncertainties associated with these things, because this is completely cap-based, this is also cap-based, this is pure analog, but in this there are compensating capacitors, in this also there are compensating capacitors. So issues are there everywhere. So what we do, we go ahead with additional designs just to ensure that everything works fine, even if there is some error. So for that, what we do? We integrate current mode DSs. Instead of voltage bias, we go for a current bias and we pump this to the pressure sensor. Okay? Then we feed this to the IA. IA output is again fed to a level shifter. This is fed to a low pass filter. Then we take this to a ADC. Then ADC output is fed to a controller. And this controller output is fed to IETSC. This is grounded. Now, as we know that we need to compensate temperature also. So what we do, we can take a tap of this, use a buffer, because otherwise loading will be there. Then we go for a level shifter, or it could be required or it could not be required. Go for a low pass filter. Then we go for a ADC. Then we feed it to the control. Okay? So with this, we have enough redundancy that even if there is some issue at circuit level, because this is pure digital, this is pure digital. The good part is this is pure digital. Okay? And I can put my memory external. I usually put my memory external. The memory chip is external. I never keep it on the same thing. I mean, you can put one more inside there, but to keep it external. And through this, we do all the control programming, everything is done. So that even if there is some variation somewhere here and there, I have enough legroom to control my performance of the circuit and I get my desired results. So this is possible. And this is there. And in fact, a similar approach was initially done by Taylor Egypt. This is a well-known company, a Swiss company, Switzerland-based company, uh, who have developed these architectures. We had also done something, a different type of architecture. Taylor has done it, and Texas has also done it. And Maxim has also done it. So we have also done this. So with this, so this is the basic approach for these sort of things. So I hope. So with this is there. Anything? So we have taken the monolithic case here. I hope I have explained about the SIP. SIP have I explained? This is the SIP case. So what is the conclusion? The conclusion is monolithic or IMAPs it is good, but it has certain limitations. And there are issues with the reliability. So nowadays what people are trying to do, if it is possible with SIP, yes, if it is possible, if SIP possible, go for it. If category 1 is possible, category 1 means this, where actually you are making a CMOS sensor and you are trying to integrate on a single chip. If this is possible, this is the best case scenario. This is the best case. Nothing better than this. Because everything lies on a single chip. You are not using any process or anything like this easy. If there are some applications where you need a separate boundary, and the boundary means you need additional guard rings and all these things, and go for category 2. But there is a situation where you cannot go ahead with category 1 or 2, and if category 4 is possible, then go ahead with that. If nothing is possible, then go for category 3. So the sequence should be cat 1, cat 2, cat 4. So this is what industry and all leading institutes, they follow this sort of approach. When you are trying to build specific circuits around sensors, it could be CMOS, it could be MEMS, it could be NEMS, it could be anything, it doesn't matter. Okay, I think I am done from my side. If you have any questions or anything, you can ask.
Yes, please, if you have any questions, you may type in the chat box. Dear participants, if you have any questions, please type in the chat box. Yes, Yuvraj, please ask the question. What is the question? Please type in the chat box. Yuvraj Singh, what's the question? Please type in the chat box. Can you hear me? Am I audible? Sir,
TTL, why we should focus CMOS? Because of just the power. No, it is not just power. It is, see, Uh, we CMOS scaling. See, scaling the way we have gone ahead, we are trying to move everything towards digital dominant circuits. And in digital dominant circuit, the only way to save power is scale down the supply voltage. So the designs are not more towards analog. It is more like you have made a digital